All right, guys, sorry I couldn't be here in person, but I am here via technology. So let's get this lecture started on formula writing and nomenclature. Nomenclature is just a fancy word that means naming. So we're going to take a look at chemicals, how we write their symbols, and also how they're named. All right, I do apologize for the formatting. When PowerPoint gets into this recording system, it screws up with the subscripts and the superscripts. So the formatting is going to be off, but on your note sheet, it should be perfectly fine. All right, we're going to start off with the easier formulas, and that's for ionic compounds. Now, remember, ionic compounds are always made up of a metal and a non-metal. Cations are the metals and anions are the nonmetals. And if we remember from regular chemistry, metals always lose their valence electrons, and so they'll become positive charges. And nonmetals or anions will always gain electrons, right? And so they're going to become negative charges. So ionic compounds always have a positive and a negative ion coming together. So in their chemical formula, the sum of the charges must cancel. Okay, so that's the clue, that's the key for ionic compounds. The sum of their charges must cancel. So they always, all compounds, okay, must be charge neutral. That's a huge clue right there as to, when you're writing the formula for an ionic compound, you can always check to make sure that the charge is neutral. So let's take a look at these three examples. We've got RbCl, rubidium chloride, on the very left. If we look at your periodic table, rubidium is in that first group, and so rubidium is going to have a positive 1 charge when he loses that valence electron to make a bond. Chlorine, on the other hand, is on the other side of your periodic table. He is in group 7, and remember, he only needs 1 more electron, right, to fill up his valence shell, and so he's going to gain an electron and become a negative 1 charge. All right, so we can add them together and say, hey, +1 and a -1 added together equals 0. So in the formula for rubidium chloride, it's just RbCl because all you need is 1 of each. 1 rubidium is going to cancel out 1 atom of chlorine because it's a give and take with just 1 electron each. Okay. Now the middle example is going to be slightly more complicated. First, we're working with magnesium. Magnesium is in group 2. And so he's got 2 valence electrons that he has to give away in order to make an ionic bond, right? So he's going to have a +2 charge when he's making the bond because he's going to give those 2 valence electrons away. Now chlorine, we just talked about. He's in group 7, and he only needs one valence electron to fill his valence shell. So he can't take the 2 from magnesium. So chlorine is going to have a -1 charge. He's going to gain the extra electron. Remember, electrons are inherently negative. So if you have more electrons, your overall charge is going to be negative. All right, so now we can see that magnesium's a +2 and chlorine's a -1. And if we add those charges together, okay, this time we don't get 0, right? We have a positive 1 charge left over. +2 plus a -1 is +1, right? So it's not charge neutral. So what that means is we need another chlorine to come around, right? We need another chlorine to come around to eat up that other +1, right? So in essence, magnesium's got 2 valence electrons. He's going to give 1 to 1 chlorine and the other to the other atom of chlorine. And then we get charge neutral. Okay, so that's kind of the idea behind being charge neutral. We need to make sure that all of the valence electrons that are given away are taken by other atoms and following the rules of their how many they gain, how many they need in order to fill their valence shell. All right, so that's kind of the long-winded explanation. Here's a shortcut. All right, we all like shortcuts. Here's a shortcut for doing ionic compounds, and I'm going to actually explain it to you in the next slide as well. But magnesium's got a +2, chlorine's got a -1. All right, this 2 we can just crisscross. Okay, we can give it to the chlorine on the other side. All right, and the 1 can go to magnesium, and so we end up with MgCl2. All right, and this 2 is there because that was the charge of magnesium. So that's going to be an example of a shortcut, okay, for ionic compounds. So let's see how that works with our last example here, aluminum selenide. So again, if we take a look at the periodic table, aluminum is in group 3. So that means he has 3 valence electrons. In order to make a bond, he needs to give away all those 3 valence electrons. So he's going to lose 3, which means he's got 3 more protons in his nucleus than he does electrons. So overall, his charge is a +3. Selenium, oh no, that's not selenium. Hello, it's sulfur. This is aluminum sulfide. Duh. All right. Sulfur is in group 6. And so if we take a look, he only needs 2 more valence electrons in order to fill his valence shell, right? So he's going to gain 2. So that means when he gains 2, now he's got 2 extra electrons compared to the protons in his nucleus. And so he's going to have an overall -2 charge. Well, again, if we add up a 2 plus a a 3 plus a -2, right? So 3 plus -2, does that equal 0? Nope. We still have 1 left over, right? So is not charge neutral. So what we'll do is we'll crisscross. We'll take the 3 and we'll put it down by the feet of sulfur, and we'll take the 2 and we'll put it down by the feet of aluminum, and boom, you have your formula Al2S3. And this crisscross thing works every time. Okay, one way to kind of check yourself is to say, hey, I've got 3 atoms of sulfur, and each of those are in -2 charge. So 3 times 2 would be overall a -6, okay, for all of the sulfur atoms. Likewise, aluminum, we have 2 atoms of aluminum, each having a -3 charge, and a +3 charge, and so 2 times 3 is a +6. Now we can see that a 6 plus a -6 definitely equals 0. All right, so that is how we write formulas for ionic compounds. Having a metal atom that's positive and a non-metal atom that's negative, because he's going to be gaining those electrons that the metal atom gives away. All right, so like promised, here's the crisscross method in kind of a written explanation. So writing for monatomic ions. Monatomic means just kind of one atom, one type of atom. We'll see how that differs in diatomic or polyatomic ions in just a few minutes. But here's how you do it. You're going to write the symbol for the metal and its charge, followed by the symbol of the nonmetal and his charge. So if we're working with aluminum oxide, okay, so down here at the bottom, we're going to have aluminum with his charge of +3, right? And oxygen with his charge of -2. All right. And the next step is to use the magnitude of the charge on each ion without the sign. So what that means is that you're not taking the negative part of the 2 with you. You're just using the absolute value, basically. And you're going to put that down as the subscript for the other ion. All right, so here we saw you take the 2 from oxygen and put it down by the subscript of aluminum. And then for aluminum, we take the 3 and we'll put it down by the subscript for oxygen. And now a lot of times, or sometimes, you want to make sure that you reduce the subscripts to the smallest whole number. So here, a 2 and a 3 you can't reduce anymore, but sometimes you may get a 4 and a 2, which you could reduce down to 2 and a 1, right? So make sure you reduce your subscripts to the smallest whole number, and then you can check yourself to make sure that the sum of the whole compound equals 0, okay, or that they cancel each other. So again, just like we saw previously, we have 2 atoms of aluminum, each having a positive 3 charge. So that means that's a positive 6 on that side. And then for oxygen, we have 3 atoms of oxygen, each having a negative 2. And so that's a negative 6. So if we add 6 plus a negative 6, we end up with 0. So we know that that is correct because it's charge neutral. All right, so let's take a look at some more examples here. So have your periodic table handy as we go through some of these. We're going to go through the first 3, and then I'll leave the other 2 to do on your own. So the first one is magnesium. We take a look. The first thing we do is we write the symbol for magnesium along with its charge. So magnesium is in group 2. He's got 2 valence electrons, so that means he's going to lose those 2 and become a positive 2 charge. Oxygen is in group 6. He has 6 valence electrons. In order to fill up his valence shell, he needs 2 more, so he's going to gain 2. So he's going to become a negative 2 charge. Now we take a look at the charges. A plus 2 and a minus 2, if we add them together, definitely equals 0. So what that means is that all we need is 1 of each. 1 magnesium, 1 oxygen, and that is our formula for magnesium oxide. All right, let's take a look at the next one, aluminum, Al. If you look for aluminum, he's in group 3, meaning he has 3 valence electrons. In order to bond, he needs to give away those 3 electrons, so he'll have a plus 3 charge. Nitrogen, on the other hand, is in group 5. So he has 5 valence electrons. In order to get that full valence shell of 8, he's going to need 3 more. So he's going to gain 3 electrons and become a negative 3 charge. So again, if we have a plus 3 and a minus 3, that adds up to 0. So in this case, our formula is just, again, 1 of each, AlN, aluminum nitride. All right. Let's do one more. We've got gallium. Just like aluminum, gallium is in group 3, so he's going to become a plus 3 charge when he loses those 3 valence electrons. And this time we're hooking him up with selenium. That's selenium. Selenium is in group 6, and so he has 6 valence electrons. He just needs 2 more, so he'll gain 2 in order to become a negative 2 charge. Now when we add these charges together, a plus 3 and a minus 2, okay, we're going to have a plus 1 left over. So this charge, or when we take 1 of each of these atoms together, they do not cancel the charges. So at that point, we need to say, hey, let's do the crisscross. So we'll take the 3 from gallium and put it as a subscript for selenium. And we're going to take the 2, remember it's just the magnitude, all right, the, what's it called, absolute value, right? And so we'll put that down as the subscript for for gallium. So when we put it together, we're going to have Ga2 Se3 for gallium selenide. All right. So it makes sense that we just take the 2 and not the negative, because if we had a negative here, I mean, you can't have a negative number of atoms, right? If the atom doesn't exist in the compound, then it wouldn't be there anyways. So that's, kind of a common sense factor with the negatives. Never bring the negatives down to subscripts, because you can't have a negative number of atoms in a compound. Okay, so before, like I said, we were working with kind of one type of metal atom and one type of non-metal atom, and we call that monatomic ions. And so now we're going to take a look at a group of atoms that are called polyatomic ions. And so poly just means many, so many atom ions. That basically is ions that are composed of a group of atoms instead of just a single kind of atom. All right, and so these groups of atoms have an overall charge to them. So in the front of your lab manual, actually, no, not in the front of your lab manual, in, I believe it's lab number 4, the Nomenclature lab, there is a whole list of common polyatomic ions that we're going to be familiar with and use during this semester in chemistry. So that will always be given to you. That'll always be handy for you. So luckily you don't have to memorize any polyatomic ions. You just know how to use that list and figure out what their charge is and what to do with these numbers. Okay, but here's a few examples. We have acetate, which is the group that's made up of 2 carbons, 3 hydrogens, and 2 oxygen atoms, and as a whole group, that has a -1 charge, has an extra electron. And then nitrate is a group of nitrogen hooked up with 3 oxygen atoms, and again, it's got a -1 charge overall. And then last but not least, for this example, is chromate, chromium with 4 oxygens attached, and when those get together, they've got 2 extra electrons. So that's a -2 charge. A lot of polyatomic ions are going to have negative charges, but there are a few that do have positive charges. Ammonium being one of them, which is NH4 with a +1 charge. Okay, so let's take a look and see how the formula writing works for compounds that have polyatomic ions. So down here, we've got calcium nitrate. So we can see calcium is hooked up with the nitrate group, NO3. And so basically it's going to work the same way. Calcium has a +2 charge because he's in group 2. We just saw that nitrate has a -1 charge. And so again, if we add up a +2 and a -1, it doesn't equal 0. So we're going to do the same crisscross method. Okay, we'll take the 2 and we'll put it down by the feet of nitrate. And we'll take the 1 and put it down by the feet of calcium. Now, when you are putting the subscripts by a polyatomic ion, use parentheses. Okay, so use the parentheses. You can see that we put the 2 on the outside of the parentheses here because you need 2 whole nitrate groups. Okay, the whole thing. You need 2 of those in order to cancel out the charge on calcium. So make sure you use parentheses when you're working with polyatomic ions. All right, let's take a look at the other example here. We've got sodium phosphate. All right, so sodium has a +1 charge, right? He's in the first group. Phosphate, if you look on your polyatomic ion list, is going to say a -3 charge. So again, if you add up a +1 and a -3, it does not equal 0. And so we have to do the crisscross method. We're going to take the 3 and put it down by the feet of sodium, right? And then we're going to take the 1 and we're going to put it down by the feet of phosphate, right? Ones, you've probably noticed, just like in math, ones are kind of assumed or go invisible, right? So just like in math, you don't have to put 1x minus 3. You can just write x minus 3. So similarly, when we're pulling that 1 down from the charge of sodium, okay, down here, it just kind of goes away, it disappears. We don't have to actually put the 1 down there, okay? Okay, so here on this slide, we've got exactly what I was just explaining, just written down in words for you later to reference. So again, when we're working with ionic compounds with polyatomic ions, we're going to write the symbols for the metal ion, followed by the symbol for the polyatomic ion in parentheses. Remember, use parentheses. And you're also going to put their charges. Then if their charges don't cancel out to be 0, you're going to use the magnitude of the charge on each ion as the subscript for the other ion. Just like last time, reduce the subscripts if possible and check to make sure that the sum of the charges is 0. So if we take a look at this last example here, we've got calcium nitrate. So calcium is in group 2. He's going to have a positive 2 charge, and nitrate is a negative 1 charge overall. So we can see if we add up a positive 2 and a negative 1, we end up with positive 1 left over. So it does not equal 0. So we're going to have to do the crisscross method. We're going to take the 2 from calcium and put it down outside of the parentheses for the subscript of nitrate. And we're going to take the 1 and we're going to put it down here by calcium. But then again, remember, you can always drop the 1 subscript because it is always assumed. Now, if we add up the charges that we've got now, we've got 1 atom of calcium with a +2 charge. So that means the metal atoms add up to a +2 charge. And we've got 2 groups of nitrate. Each group is a -1 charge. So that means the anions are going to add up to a -2 charge. Now, if we add the 2 together, +2 and a -2, we end up with 0. So the charges cancel. We're going to do 2 more examples just to make sure that we've got this down. So we've got sodium sulfate. Sodium, the first thing we have to do is write out its symbol. So sodium is Na, and if we look on the periodic table, he's in group 1. So he has 1 valence electron that he's going to give away when he makes a bond, and so he will end up with a positive 1 charge. Now sulfate, if you take a look, is SO4. And that group altogether, we'll put in parentheses, and that group altogether has a -2 charge. Okay, so if we add up a positive 1 and a -2, it is not going to equal 0, right? So that means we have to crisscross the charges. We're going to take the 2 from the sodium charge, put it down by take the 2 from the sulfate charge and put it down by sodium as his subscript, and we'll take the 1 from sodium and put it down here for the subscript of sulfate. And so as a final answer, we'll have Na2SO4, sodium sulfate. Okay. All right. The second example is potassium phosphate. Okay, so if we take a look, potassium's symbol is K. He also is in group 1, so he's going to have a positive 1 charge. And phosphate is the group PO4, and he's going to have a -3 charge. So if we add up a +1 and a -3, it does not equal 0, right? So let's crisscross those charges. We're going to take the 1 from potassium, put it down by phosphate, and we'll take the 3 from phosphate, put it down by potassium, and we're going to end up with K3PO4. Boom. Potassium phosphate. All right, so that was formula writing for ionic compounds. If you have any questions, make sure that you ask when I'm back, and I'll be happy to answer any questions you have. Make sure you practice, go through the book. There's a whole section on it. Do the practice problems from that section just to make sure that you know what you are doing. All right, let's move on to nomenclature. And like I said earlier, nomenclature is just a fancy word for names, okay, or naming compounds. So scientists use, or chemists have a system for naming compounds. There's the common name, okay, versus what we call a systematic name, which is like the chemical name. So common names are, layman's terms, kind of names, I should say, for common substances. So for example, H2O, the common name is water, right? That's what we, speak of that substance every day. I need a drink of water. my shower water was too cold, right? We're not saying I need a drink of H2O, or I need, my H2O to be warmer or whatnot. So that's our common name for the substance H2O. Now, scientists also have a systematic name, and the systematic name for H2O is dihydrogen monoxide. It is more specific in its name as to what kind of atoms are in it and how many. All right, so a lot of systematic names will have the element names in them, okay, along with how many atoms of each. So systematic names have rules to follow. Okay, so as soon as you understand the rules, the systematic names are pretty simple to kind of go by. Common names, on the other hand, have to be learned only through familiarity, okay, or kind of memorization. So, for example, the flammable family of hydrocarbons, okay, have common names as well. You've probably heard of them: methane, propane. Okay, butane, those are all common fuels that we use in stoves or flamers, to burn and make flame to cook with or heat something, right? So methane, its formula is CH4, ethane is C2H6, propane C3H8, and butane C4H10. Okay, so we can see that the name here has pretty much nothing to do with the type of atoms or how many there are in each of these compounds. Now, if we took a look at the systematic names, this first one would be carbon tetrahydride. The second one would be dicarbon hexahydride. Okay, so we can see that the systematic names have nice, easy rules to follow, which make learning them a lot easier than learning common names. All right, so let's start by taking a look at naming ionic compounds. So remember, ionic compounds always have a metal and non-metal. Okay, so have a metal and one or more non-metal atoms together, we can assume that it is an ionic compound. And so there's two types of ionic compounds, actually. We've got type 1 and type 2. So type 1 contains metals with an invariant charge, meaning that the charges never change. And you can look at the periodic table for it. In fact, that's what we did in all of the previous examples when we were writing the formulas. Every metal atom in groups 1, 2, okay, and 3 fall under type 1. They are invariant charges. We can always take a look at the periodic table and know exactly their charge. Okay, potassium always has a 1 valence electron, will always lose its 1, always has a positive 1 charge. Gallium always has 3 valence electrons, always loses his 3 valence electrons, always has a positive 3 charge in bonding. Okay, so those guys are type 1. Now there is type 2, which are metal atoms that can have different charges. Okay, and these fall under the transition metals, these guys in the middle, and then 2 more over here in group 4 that act like transition metals as well, tin and lead. All right, so these guys have variant charges. Their charges can vary depending on how many valence electrons they are willing to give up to make a compound. Okay, so these guys, you cannot look at the periodic table to tell exactly what the charge is. So we have to name them differently than what we name our regular metal atoms. So let's see how this works here. So we're going to start with type 1. So a binary compound just means bi means 2, right? So a binary compound has 2 different elements in it. So the basis for naming binary ionic compounds is this. We put the name of the cation, which is the metal atom, and then we put the base name of the anion, which is our non-metal atom, and then you add IDE at the end. Okay, so because the charges of these metal atoms are always the same, right? Because these guys are invariant charges, we do not need to specify what the charge is in the compound's name. So for example, we've got NABR, right? And so we're just going to write the name of the metal, Na. You look up Na and you're going to see sodium, right? And then if we look up the name for Br, we're going to see that on the periodic table, it's bromine, right? Ione. So what we're going to do is we're going to take the base name of it, the Brom, and we're going to add the IDE at the end. So instead of bromine, we're going to change it to bromide. So sodium bromide is the name for NaBr, sodium bromide. Okay. Now, let's do another example, MgO, right? If you look at the periodic table, Mg is magnesium. So we'll write out the name magnesium. All right, and then again, we take a look at the name for the anion, and O is oxygen. So we're going to take the base of that, which is the oxy, and we're going to add IDE at the end. Okay, so we're going to change the gin and we're going to add IDE. So we have oxygen. I'm sorry, not oxygen, we have oxide. All right, so the MgO is magnesium oxide. Now for some of them, they might sound a little funny. Okay, so you kind of have to play with them or ask so you can get familiar with what they are. So for example, like nitrogen is nitride. Sounds weird, but it's nitride. Selenium is selenide. All right, so some of them sound kind of funny, but as soon as you get used to them, you should have no problem with that. So let's do a few examples here of type 1 binary ionic compounds. So MgF2. Okay, so here we've got Mg. So we look on your periodic table for Mg, and you're going to find that that's magnesium. So we'll write out the name magnesium. Right, and then F is fluorine on your periodic table. So we're just going to change that ending from INE to IDE. So fluoride. Magnesium fluoride. Easy, easy. The next one, Al, is aluminum. So we'll write out the name aluminum. And then S is sulfur. So it's not sulfuride. We're going to take the root, which is sulf, and we're going to add IDE, sulfide. So aluminum sulfide is Al2S3. Last but not least, we have Na3N. So Na, if you look on your periodic table, is sodium. And N, plain old N, is nitrogen. So we're going to take the root of that, nitr, and we're going to add the IDE at the end. So we're going to take off the ogen, and we're going to add IDE, and this is called sodium nitride. All right, so that was type 1, where we had metal atoms that always have the same charge no matter what. They have invariant charges. Now, type 2 is where we're going to have metal atoms that have varying charges, depending on, I like to say mood. Obviously, it's not a mood since they are inanimate objects here. But that's kind of how I like to refer it. Sometimes they want to share, one valence electrons. Sometimes they'll share 2 valence electrons. Depends on their mood. So let's take a look and see how we have to name these type 2 slightly differently than we have to name type 1. All right. So the big key is, because the charge of the metal ion, okay, is not always the same, you must specify the charge in its name. All right. And so to do that, we're going to write the charge. It's very specific. These guys are, very, what's it called, high maintenance kind of. So in order to specify the charge is going to be in Roman numerals in parentheses following the name of the metal. So I kind of like to think of it as its middle initial, kind of. Okay, so middle initial. Put that in parentheses. All right, so in order to figure out its charge, this is key as well. In order to figure out its charge, you have to uncrisscross the formula in order to figure out the charge. for that particular compound. Okay, so it can be a little tricky. So the first thing you have to do when you're taking a look at a compound like this, okay, FeCl3, is you have to look and say, hey, is this metal and variant metal? Is it a transition metal or one of those tin or lead? If so, like iron, take a look at iron. Iron is on the top row of the transition metals. That means you have to name him differently than what you would name him if it was a type 1. So we're going to put the name of the metal atom. Okay, so we'll write out Fe as iron. And then we have to put the charge, right? And so in order to figure out the charge, we have to uncrisscross. So this 3 here is there because remember, we crisscrossed it from the charge of iron. So that 3 over by chlorine is there because it was the charge on iron. So if we uncrisscross, we'll know that the iron has a positive 3 charge. So we need to put that as the middle initial in Roman numerals right after its first name. Okay, so in parentheses, we have Roman numeral 3 for the charge on ion. And then the rest of it is just the same as the other one, the base of name of the anion plus the IDE ending. So instead of Cl on the periodic table is chlorine, instead of chlorine, it's chloride. So we add IDE and we have the full name, iron 3 chloride. All right, so let's take a look at another example. Here we have CrO. So if we look up Cr on your periodic table, his name is chromium, right? And if we look up O on the periodic table, that's oxygen, and so his last name is going to be oxide. So the only thing we need to figure out is what is the charge on chromium, right? And so if you kind of looked and, did the whole uncrisscross thing, you'd say, oh, it's got to be a +1, right? Because there's, a 1 down here essentially for its subscript. But that would not be correct, okay? And let me show you why. Anytime you're working with a ionic compound whose anion is in group 6 or 5, you're going to need to make sure that you are paying special attention, okay? Because oxygen inherently has a -2 charge, yes? He's in group 6. He always has to gain 2 more electrons in order to fill his valence shell. So that means he always will have a -2 charge. So in order to cancel out and make this whole compound neutral, chromium must then have a +2 charge, not a +1 charge like we thought if we were uncrisscrossing, right? So you have to make sure that you're paying special attention if there are no subscripts, to double check and make sure that it's not, a 1. Okay, sometimes it might be a 1, but a lot of times it's not, all right? Especially if you're working with anions in group 5 or 6. So in this case, chromium is chromium 2 oxide. Okay, again, the chromium has to be a +2 in order to cancel out the -2 charge that oxygen always is. All right, let's take a look at some more examples of naming ionic compounds. So here we've got PbCl4. Now Pb, if we look on our periodic table, his name is lead. And if we look at him, he is one that has a variant charge. He's in group 4, right under tin. And so he's going to act like those transition metals. So what that means is that we need to have his charge in parentheses as his middle initial, right? So in order to figure out the charge, we have to uncrisscross. Luckily, he is hooked up with chlorine, and chlorine always has a -1, right? So we don't need to worry about that trick with like we had to do with chromium and oxide. Here we can just straight up uncrisscross. So this 4 was here because it was the charge on lead. So our middle initial is Roman numeral 4 in parentheses. Now the last part of it, his last name is chlorine. Instead of chlorine, we're going to add the IDE ending and we're going to call it chloride. So lead 4 chloride is this name. Now the second one is COO, right? So C little o, if you look on your periodic table, is cobalt, and you'll see that it's in the transition metal section on your periodic table. So this guy has a variant charge. So we need, again, to have his charge in parentheses, okay, as his middle initial. So here he's hooked up with oxygen, right? So this guy's last name is oxide, and that's going to give us a red flag because oxygen is in group 6. So we need to make sure that we keep in mind that oxygen is a -2 charge always. So if we had one atom of oxygen and it's a -2 charge, the only way to cancel the charge on oxygen to have this a neutral compound is if cobalt was a +2 charge. So this is one of those trickier ones. So this should be cobalt 2 oxide. All right, let's take a look at the next one. Next one is SR. If we look on your periodic table, SR is strontium. Now, strontium is in group 2, right? So does he need the Roman numeral with his charge in it? Your answer should be no, because anybody in groups 1, 2, and 3 don't need their Roman numeral charges, right? So we can just say strontium, and then Br is bromine, which will change to bromide. So strontium bromide. You don't need the parentheses or anything like that in this one. So let's take a look at our last example here. We've got nickel nitride. All right. So Ni is nickel. He is a transition metal. So first off, let's put his name down, nickel. And you'll find that he's a transition metal. So transition metals, remember, need their charge in parentheses. And in order to find his charge, we have to uncrisscross, because remember, those transition metals have variant charges. So we have to crisscross. So this 3 down here, just kidding. This 3 right here is the charge of nitrogen, right? Because nitrogen has 5 valence electrons. He'll need to gain 3 more in order to make a neutral bond. And so that 3 comes from the -3 charge on nitrogen. So down here is like a 1, right? So down by the nitrogen foot is like a 1. So if we uncrisscross, that must be the charge of nickel. So nickel is just a 1. So we have nickel 1, and then we have to do nitrogen, but have his ending with IDE. So it's going to be nitride. Nickel 1 nitride is the name of Ni3N. Okay, so let's take a look at the next type of naming compounds containing polyatomic ions. This is the same kind of procedure as other ionic compounds, except if there is a polyatomic ion in it, you're going to keep the name of the polyatomic ion. You're not going to end his name with IDE. Okay, so let's take a look at some types of polyatomic ions. So most polyatomic ions are what we call oxyions. They're anions that contain oxygen, right? So if you look at the polyatomic ion list from your lab manual, you'll see a lot of them are hooked up with oxygen: nitrate, nitrite, sulfate, sulfite, chlorate, chlorite, hypochlorite, all those guys, carbonate, chromate, all of them are oxyions containing oxygen. Now, sometimes there might be a different number of oxygens that can be hooked up in a polyatomic ion, okay, with the same, non-metal. For example, NO3, nitrate, right, versus NO2, which is nitrite. So we can see we have a nitrogen hooked up to oxygens, a different amount of oxygens. In nitrate, there's 3 oxygens. In nitrite, there's 2 oxygens. So the name actually kind of gives a clue as to how many oxygens there are. If it has an ATE, that means there's more oxygen atoms than the other option. Okay, so for example, NO3 has more oxygen atoms than NO2. So NO3 is going to end in ATE. That's why it's nitrate. ITE means less oxygen atoms. So NO2 has less oxygen atoms than NO3, and that's why he ends in ITE as nitrite. Okay, now that's if there's only two options, but there's some polyatomic ions that have 4 options, like the chlorite group. Okay, so if there's less than the ITE, we are going to put a prefix of hypo. Hypo means less than the ITE. So for example, if there was an NO, okay, polyatomic ion, there's not, but if there was an NO, we would say hyponitrite. Okay, we'd put that hypo in front and still end it with ITE. Now the last option is if there is more than the ATE. Okay, so if hypothetically speaking there was an NO4, right, then we would say per nitrate. Okay, because we'd add that per prefix before. Okay, so here's an actual example down here of 4 polyatomic ions that are in the same family. We can see ClO, okay, with 1 O, we call hypochlorite, okay, because it has the least amount of oxygens. Then the next one has 1 more oxygen, has 2 oxygens, and so we call it chlorite. We forget the hypo part, we just call it chlorite. The one with 3 oxygens, okay, gets the 8 because 8 means more oxygens than ite. And then finally, the one with 4 oxygens, all right, we have that per prefix along with the ATE suffix, so perchlorate. So that's how it's going to work with some polyatomic ions. So the main thing that you have to remember is that you use the name of the polyatomic ion whenever it occurs. So you're never going to change the polyatomic ion's name to IDE. Never do that. So let's take a look at some examples of naming them. So the first one is NaHCO3. So we can see that there's a polyatomic ion because we've got more than 2 types of atoms in this compound, right? We've got our sodium metal, and then we have a group of nonmetals that are hooked up to this sodium. So those guys are the polyatomic ions. A lot of times you'll find them in parentheses. Boom, okay? But not always. So let's take a look at Na. Na from our periodic table is sodium. So we're going to write his name. And to get the polyatomic ion, remember we have to just look them up on the list. You don't have to memorize these, but you just have to look them up on the list. So here is HCO3. Okay, so we can see the name is hydrogen carbonate. So this guy is called sodium hydrogen carbonate. Boom. Done. Okay, we don't have to change anything to ITE. Sodium is not a transition metal, so we don't need his charge. So bam, just sodium hydrogen carbonate. Now, that guy is found in baking soda. Okay, that's why this picture is there. All right, the next is calcium. Okay, Ca is calcium. We can look on our periodic table. Ca is calcium. And then we just have to look up what CO3 is. CO3, it's right here, is carbonate. So again, we just use his name, calcium carbonate. And that's the main ingredient in Tums and other antacid chewable tablets. All right, last but not least is the last one, NaNO3. Na we already seen is sodium, so we can write the name sodium. And then NO3 we can find on our list right here. That guy is nitrate, so we just call him sodium nitrate. Done. All right, so that's how we name things with polyatomic ions. Use the name of the polyatomic ion. You don't have to change its ending to ITE. Okay, so that kind of brings us to the end of naming ionic compounds. Ionic compounds, remember, have a metal and a non-metal hooked up together, okay, to make a bond. Then the last half of this is going to be naming molecular compounds. And molecular compounds come from the formation of two or more nonmetals. Okay, so when two or more atoms from the right-hand side are coming together to make a bond, we call that a molecular compound. And there's different naming rules for them. Okay, so in binary compounds, or compounds that have two elements to them, you're going to see that in the molecular compounds, you're going to use prefixes. Okay, so we're going to see a prefix, and then we'll see the name of the first compound, and then we're going to see a prefix and the name of the second element plus the IDE ending. Okay, so that's the only thing that is in common with nonmetal and metal compounds, is that unless there's a polyatomic ion, everything always ends in IDE. Okay, so molecular substances use prefixes. So it kind of gives you a big clue if you see a name of a compound that has a prefix like mono, di, tri, tetra, any of those, gives you a huge clue that that is a compound that's made up of nonmetal atoms. All right, so there is one exception to the prefix. If there is only one atom of the first element in the formula, the prefix mono is omitted. Okay, so we don't use the prefix mono if the first element, there's only one of them. Like, for example, CO2, there's only one carbon here. Okay, so we don't say monocarbon dioxide, it's just carbon dioxide. We basically, drop that mono part if it were to start with it. Okay, so in this table is all the prefix names. Mono, di, tri, you've probably definitely heard of. Tetra is 4, not quad, or quadra, tetra. But the rest are the similar geometric prefixes: penta, hexa, hepta, octa, nona, deca. All right, so let's see how this works. Let's name each of these compounds using our prefixes and the names from the periodic table. All right, so the first is CCl4. So we can see that there's only one atom of C, carbon, right? So we're not going to use mono, we're just going to write carbon. We'll drop the mono part because there's only one of them. And then Cl is chloride, okay? And then we can see that there's a 4 here. So if we look on our prefixes, that's tetra. So we're going to say carbon tetra chloride. Remember, everything always ends in IDE unless there's a polyatomic ion. And in these, there will never be polyatomic ions because these are molecular substances, which are just all nonmetal substances hooked up to, or all nonmetal elements hooked up to each other. Okay, let's take a look at the next one. Okay, the next one is CS2O. We take a look at CS. So go ahead and find CS on your periodic table. You should see that he's on the very left-hand side. Okay, so are we going to use a prefix? Your answer should be no. This guy's a metal. Haha, this is a trick question. Okay, I put this in there because you need to make sure that every time you look at a compound, you look and see if you're working with metal nonmetal compounds or two nonmetal compounds. Okay, so in this case, cesium is a metal, so we don't have to use prefixes at all. Even though there's 2 cesium atoms, this is not a prefix. We don't use prefixes because he is a nonmetal atom. So this is going to just be cesium oxide. Boom, done. Okay, no prefixes for ionic compounds. All right, let's take a look at the next one. Next one is BCl3. Okay, so boron If you find him on your periodic table, boron is just to the right-hand side of our staircase, so he's going to be a nonmetal. And Cl are also nonmetals, so this is definitely a molecular compound, so we're going to use prefixes. There's only one atom of boron, so we're going to drop the mono part, and we're just going to write boron. All right, and then the prefix for 3 is tri, and then Cl is chlorine, so we're going to change it to chloride. So boron trichloride. Last but not least, we have SF6. If we locate them on the periodic table, they're both on the right-hand side. And again, we only have one sulfur atom, so we're going to drop the mono. We're just going to put sulfur. We're going to check out the prefix for 6, that's hexa. And then fluorine is going to change to fluoride. So sulfur hexafluoride is his name. All right, so you guys definitely need to be careful when you are naming. Make sure you look on your periodic table to see what kind of elements you're working with. If it's a metal, nonmetal, that's ionic. We don't use prefixes. But if it's 2 nonmetals together, we're definitely going to use those prefixes. Okay, so the next on our list for naming is acids. All right, acids are molecular compounds that produce a hydrogen ion when dissolved in water. So we're going to learn more about acids later this semester, but we're going to learn how to name them now. So basically, acids are going to, when they mix with water, they're going to release a hydrogen ion into it, which gives it its acidity. And, the properties from that, being able to dissolve some metals and being, more harmful to your skin and body than other substances. So when we're naming acids, the H is always written first in the formula, okay, followed by one or more nonmetals. We're going to see that when we study acids, you can tell if it's an acid because it has an H out front in its formula. And then, acids have a sour taste and the ability to dissolve some metals, just like I said. So let's take a look at acids. They can be categorized into 2 groups. Binary acids contain hydrogen and just a nonmetal. Okay, so that's binary. So binary means 2. So a hydrogen and one other nonmetal. And then there's also something that we call oxyacids, all right, which again have to have a hydrogen, but then they have basically a nonmetal and oxygens as well. I'll give you a hint. It's basically going to be some kind of polyatomic ion. So an oxyacid is a hydrogen atom hooked up with polyatomic ion. So this group here, if you look at the chart down below, this column here, HCl, HBr, H2S, those guys are binary acids since there's only a hydrogen hooked up with one nonmetal. And the right-hand column are the oxyacids, where you can see the hydrogens out front, and they're hooked up with a polyatomic ion. Nitrate, sulfate, chlorate, all those guys are polyatomic ions that have oxygens in them. Okay, so when we name binary acids, okay, they always start out with the prefix hydro. Okay, so hydro something acid. So you've heard of hydrochloric acid. So we know that that's a binary compound because it always starts with hydro. So we have hydro, the base name of the metal, and then we add the ic ending, and then also the acid. So for HCl, the base name of that nonmetal is chlorine. So we have that chlorine. All right. And so we've got the prefix hydrochloric and then acid. HBr works the same way. Since it's a binary, it's only H and Br. We've got hydro to start. The base name of that nonmetal is brome, okay, for bromine. And then we're going to change that to ic, hydrobromic acid. And then last but not least on this examples is H2S. Again, there's only 2 types of elements in this one. And so we're going to start off with hydro. And then this is sulfur. So we're going to have that root word sulfur. We'll change that ending to ic. And then at the very end, we have our acid. So hydrosulfuric acid. Naming oxyacids, or the ones with the polyatomic ions, is different than naming the binary acids. Okay, so the combination of one or more hydrogen atoms with an oxy anion, okay, or polyatomic ion that has oxygens in it, is our oxyacids. So the number of hydrogen ions is going to depend on the charge, okay, of the oxy anion. So the formula is always charge neutral. Okay, so just kind of keep that in mind. Anytime you have an acid, you always want to make sure that the number of hydrogen ions is canceling out the charge of the oxy anion. Okay, this actually works for the binary ones too. In fact, in the last slide, we saw H2S, right? So the S, sulfur always has a -2 charge. So, and hydrogen has a +1 charge. So that's why we had to have 2 H's in order to cancel out the S in hydrosulfuric acid. Okay, so the same thing kind of works with the polyatomic ions. So in naming them, okay, it depends on what their polyatomic ion name is. Okay, so for example, if their polyatomic ion name ends in ITE, what we're going to do is we're going to use the base name of that oxy ion. You're going to use the base name of the polyatomic ion, and you add US. So ite changes to OUS. Okay, so it's an US acid. And then also, obviously, in order to help us recognize that it's an acid, we're going to put that acid name at the very end as well. Okay, so if we take a look at this example, HNO2, all right, this is a hydrogen hooked up with the NO2 polyatomic ion. When we look up the name of NO2 on our list, we'll see that it's nitrite. So for this guy, we're going to use that base name nitrite, okay, and we're gonna change it to nitrous acid. Okay, so HNO2 is nitrous acid. The next one, okay, is H2SO3. Okay, so when we look up SO3 on our polyatomic ion list, you're going to see that it's sulfite. So sulfite is we're going to use the base name, the sulf part. Okay, so instead of sulfite, we're going to change the ITE to OUS. So actually this is sulfurous. We're going to use the sulfur part, sulfurous acid. Okay, so we're going to use the base name of sulfur, and then we'll add the OUS to it, and then the acid at the end, so sulfurous acid. So the ite polyatomic ions always end up changing to OUS as the acid. Now that leaves us with the ATEs. Okay, the polyatomic ions that end in ATE. We'll check it out. Their name, their last name, or the ending of their name always changes as well, and they get the ic acid. So, for example, instead of HNO2, what if we have HNO3? HNO3 is, or the NO3 group is nitrate. So this guy is going to change to nitric acid. The ATE turns to IC, and then we add the acid at the end. The same thing here. Instead of H2SO3, we have H2SO4. SO4 is sulfate. So this is going to end up as sulfuric acid. Okay, so sulfuric acid, H2SO4. Okay, so let's do some practice here. We're going to start with HI. Okay, so HI, there's only two type of elements, so this is the binary type of acid. And so this one's going to start with hydro. So we're going to have hydro, and then I is iodine. So this is going to be, we're going to take that IO, we're going to add the ic at the end, so iotic, and then acid. So hydroiodic acid is HI. H2CO3, we can see there's more than just two types of elements there, so this has to be an oxy acid. In fact, if you look at your polyatomic ion list, CO3 is a polyatomic ion carbonate. Okay, he ends in ATE. And remember, all oxy acids that end in ATE get the ic name change. Okay, so this guy is going to be, instead of carbonate, we're going to call him carbonic, and then acid. The next one, again, is more than two elements. We have hydrogen hooked up with the chlorite polyatomic ion, ClO2. So since he ends in ITE, his polyatomic ion name ends in ITE, his name is going to be switched to OUS. So we're going to have chlor, and instead of ite, we're going to have OUS. So chlorous acid. Okay. The next one here is just two elements, H and P, H3P. And so this guy is going to be a binary acid. So he's going to start with hydro. And then P is phosphor. So we're going to say phosphoric. So hydrophosphoric acid. All right. And then last but not least, we can definitely see here that there's definitely more than just two elements in this acid. So this is an oxy acid. And this here, C2H3O2, is the the acetate polyatomic ion. So we're going to change that name to acetic, because remember, ATE switches to ic. So this guy is acetic acid. Boom. So we just have to make sure that we keep in mind the difference between a binary acid, one with just two elements in it, versus a oxy acid, one with a polyatomic ion, because their naming is going to be different. All right, hallelujah. That brings us to the end of our naming or nomenclature part of this lecture. And so this is just kind of summary slides. So when naming compounds, the first step is to decide whether the compound is ionic, that has a metal and a nonmetal, or whether it's molecular with two or more nonmetals, or if you're working with an acid which has an H out front and one or more nonmetals. Okay, then you have to, once you know that, then you have to follow the precise naming rules. So I've got this next slide is actually a really good summary and a flowchart that you guys can use in naming the compounds that you'll be given. So here's this big flowchart. It takes you exactly through each of the three types of compounds that we were naming in here. This here on the very left is your flowchart for ionic compounds, so you just kind of follow that. In the middle is your molecular, your nonmetals only, and then on the very right-hand side is naming acids. So you can see you just kind of follow the flowchart, and kind of go to one side or the other depending on what type of compound you're working with. So this is a really good tool when you're starting to name compounds and trying to get the hang of it. This will be a really good resource. So make sure you, if you didn't print this, make sure you do, and make sure you bring it to our next lab number 4, when we're going to just be naming compounds, naming. So make sure you bring this. Okay, so I know you're done, but we've just got a couple more slides, and this is actually a review of basic stuff that you guys learned in regular chem. Calculating the formula mass of a compound. So the formula mass is the average mass of the molecules or formula units that compose that compound. So basically it's the sum of the atomic masses of all the atoms in the chemical formula. It's super easy to do, right? You look on your periodic table and you say, hey, there's a carbon. Carbon's formula weight is 12. And, you know, then you add up the next element in the compound that you're working with. So let's see how this works. So if we've got the compound CCl4, right, it's made up of 1 carbon atom and 4 chlorine atoms, right? So we just take the mass of 1 carbon atom, which is 12.01, and then we take the mass of the chlorine atoms, 35.45, and we multiply it by 4 since there's 4 atoms in there. Then we add it together to get the final mass or the formula mass for this molecule. Okay, so it's really quite simple. Let's do these last couple of examples in this lecture, and then you guys will be, you guys can turn this off. All right, so let's take a look at the formula mass for N2O, dinitrogen monoxide. So we've got 2 nitrogens. Each nitrogen is 14.01. Okay, and then we have oxygen, which is 16.0. So if you add those together, we do 28 plus 16 is 44.02. Okay, atomic mass units, AMUs. Boom. All right, our next one is O3. And so this is super easy. We just take, there's 3 of them. Each oxygen is 16. And so 3 times 16 is 48 atomic mass units. Water is H2O. So we have 2 hydrogen atoms, each 1.01. And we're going to add our 16 to that. And when we add those together, we end up with 18.02 AMUs. Right? And then last but not least, we have magnesium sulfate. This will be the biggest one. So magnesium is I believe 24. And then we've got sulfur, which is 6. Nope, just kidding. It's 32. All right, this is 32. And then we have 4 oxygens. 4 times 16 is 64. So if we do that real quick, 24, 32, 64 is about 120. Okay, atomic mass units. Okay. So it's really easy. You just add them all up on the periodic table and you've got your formula mass. All right, we're done. We're done. Hallelujah. You can shut this off now and get started on those practice problems.